Kim 107. This is our second video in chapter 3. We're talking about fossil fuels. So we just finished talking about coal, the solid fossil fuel. Now we're going to talk about petroleum oil, which is the liquid fossil fuel. Now, these pumps bring oil up from down below the ground, and they're all over West Texas, which is where I grew up. So I'm very used to seeing these around where I lived. Now, petroleum oil is very popular now because it's easy to transport since it flows because it's a liquid. So it's way more popular than coal because no one wants to shovel coal in their car. They like to just pump the liquid gasoline in. But it is more expensive, so we pay for that ease of transport. Petroleum is about 48 kilojoules per gram versus high-grade coal, which is about 30 kilojoules per gram of energy. So measuring energy, we actually get more energy per gram out of petroleum than we do coal. So petroleum comes out of the ground crude. You can call it crude oil, and it has to be refined before we can use it. Now, the United States does not have enough oil, so that's different from coal. We don't have enough oil in our country, so we have to import it. Where do we get our oil from? What do you think? Name a country or two. Did you say the Middle East? Yeah, most people say the Middle East, but look, actually, 16% of our oil comes from Canada. 12% comes from Saudi Arabia. But then 12% also comes from Venezuela, 12% comes from Mexico, and the next largest country is 9% from Nigeria. So it's not just the Middle East where we get our oil. We get it from a bunch of different sources, and those are the top 5. So that may have surprised you. So crude oil comes in a mixture of many of the different hydrocarbons. Hydrocarbons mean hydrogen and carbon are in there. So crude oil is mostly hydrocarbons. So compounds with H and C atoms, hydrogen and carbon. And hydrocarbons typically have anywhere from 1 to 60 carbons per molecule. So we have little bitty hydrocarbons that just have 1, 2, or 3 carbons in them. And then there's giant hydrocarbons that have 50, 55 carbons in them. Now, oil has less sulfur than coal. So when we burn it, we get less SOx. So that's a good thing. Although we still get a bunch of stuff we don't want when we burn oil, so it's not great. So all these hydrocarbons are all mixed together. We need to separate them to be useful. So to separate them, we use distillation. Remember that, distillation. That's where you heat up the crude oil until it starts to boil. Now, the littlest hydrocarbons will boil off first. And so we can collect the vapors and condense them back to liquid. Then the next biggest will boil off first, turn into vapor, rise up, and we'll collect it, and so forth until we separate all the hydrocarbons from each other. So again, the smallest hydrocarbons go up the distillation tower the highest. The big hydrocarbons stay down lower. So the more carbon atoms, the higher your boiling point. So you have to have more heat to boil a big hydrocarbon than a little hydrocarbon. So this isn't the best picture I know, but it's kind of a distillation column. So we have our crude oil, it goes into the boiler and we boil it. And then the little hydrocarbons rise up to the top, up where it's blue. The big hydrocarbons stay down at the bottom where it's red. And then there's everything in between. So it's hard to see this, but at the top, we're getting 4 carbons off. So that would be methane, ethane, propane, and butane. Then the next level, we can get off naphtha and gasoline. The next levels down, we get off our kerosene. Next level down, we can get some biodiesel and some gas oil. And then lower down are the big ones, and they're not really useful to us. So if you see there, it says cracking unit. We send them to a cracker, a cracking unit. And we'll talk about that in just a minute. So anyway, to separate hydrocarbons from each other, we use distillation, and we'll boil off the hydrocarbons and separate them from each other. And it's the little ones which are the most useful. The big ones are not useful. So hydrocarbons are called alkanes. The simplest ones are. So alkanes have single bonds in them. So we learned about that in chapter 2, right? When we talked about Lewis dot structures. So we know what single bonds are. And we see a picture here for methane, ethane, propane, and butane. So we see carbons in the middle with hydrogens around the outside, and we see all single bonds in our Lewis dot structures there. And we see pictures of what the molecules look like. If you look at methane up there, that one we should know its shape. Look at its shape. It's tetrahedral, right? It's tetrahedral. So we learned the shape for little molecules like methane. CH4 is tetrahedral. So a typical barrel of crude oil contains 19.2 gallons of gasoline, 10 gallons of diesel, 3.8 gallons of jet fuel, 1.7 gallons of heavy oil, 1.7 gallons of methane, ethane, propane, and butane, 7.3 gallons of other stuff that we tend to make plastics, pharmaceuticals, and fabrics out of. It is estimated we will run out of oil in this century, so in your lifetime. The U.S. Department of Energy predicts peak oil will be between 2026 and 2047, meaning after that it's going to get way more expensive and we're not going to have very much of it. So peak oil is the point in time in which the world will reach a maximum of oil extraction. Afterwards, oil will decline. In other words, we're going to have to switch to something else whether we want to or not. And we need to because it's so polluting. So we need to switch, and the fact is we're going to have to. So we're going to have to switch anyway. So cracking, let's get back to cracking. The small hydrocarbons like octane, which is in demand for gasoline. In other words, carbons less than 12. Those are very much in demand. So they're useful. We can take them from the distillation and use them. But the larger hydrocarbons aren't very useful. So we need to break them into the smaller ones that are. And we do that in a cracker. So gasoline is a mix of hydrocarbons with typically 5 to 12 carbons. 8 is, we'd call octane, has 8 carbons. So what happens in the cracker? Well, look at this little reaction here. We have C16H34, and it's going to break down when we have high heat in the cracker to C8, H18, and C8, H16. So 8 carbons is useful. 16 carbons, not so much. So in the cracker, we just heat the crap out of it, and it'll break down into smaller and smaller hydrocarbons. Does anyone remember leaded gasoline? Yeah, we had lead in our gasoline. I believe it's because it helped with knocking. That was finally banned in the United States in 1996 by the Clean Air Act, however. So used to, when I was a little girl, I remember going to the gas station and it would be like leaded and unleaded. Now everything is unleaded. So we don't have leaded gasoline anymore because lead's a pollutant, right? It's a pollutant. We don't need exposure to lead. So we did ban leaded gasoline in 1996. So there's a picture, not a very good one, I know, of a cracker. It heats the large hydrocarbons to about 400 to 450 degrees Celsius, which is really hot, okay, way high in Fahrenheit. And we crack them into smaller ones. So it cracks the big hydrocarbons into little ones that are more useful. The cracker. Don't confuse a cracker with the distillation process. 2 very different things. Make sure you remember both of them and remember what they are. Distillation separates the hydrocarbons in crude oil from each other. The cracker takes the heavy ones, the big ones, and breaks them down into the more useful, smaller hydrocarbons. All right, so that's our talk about the liquid fossil fuel. Let's talk real quick about natural gas, the gas fossil fuel. Natural gas is about 90% methane. Remember that. Natural gas is mostly methane. Methane, which is CH4. Remember that as well. CH4, the simplest hydrocarbon. Methane provides heat for about 2/3 of the homes in the United States. Not so much in Arizona. We don't have a lot of natural gas, but other places, they do use natural gas for their heaters, their dryers, and the water heaters are often powered by gas. But again, in Arizona, we have a lot of all-electric homes, which is unusual, actually. Natural gas burns cleaner than coal or oil. It has less impurities, but it still produces things we don't want. It doesn't have any mercury, so that's good. And it doesn't produce a lot of NOx and almost no SOx. So it's better than coal or oil in that respect. But it still makes a whole bunch of CO2, and that's not good. It makes a little less than oil or coal, but it still produces a lot of CO2, which is the greenhouse gas, which we'll talk about in chapter 4, and that's not good. We don't want to make CO2. So this is not the answer. We don't need to all switch to natural gas. We need to not use it either. It's a fossil fuel, still makes pollutants, still makes greenhouse gases. We gotta switch to something else. Fracking. Now, fracking is fairly new because they're getting desperate for ways to find fossil fuels since we're running out of them. So fracking involves drilling down into shale, that's a type of stone in the ground, that contains natural gas deposits about 1 to 2 miles down. They inject this cocktail that they won't tell us what it is. It's water and other things, and we inject it down into the shale under pressure, and it creates cracks and makes the gas come up to the surface. So we collect the natural gas. So we're putting these substances down in the groundwater as well. So the environmental impacts include the risks of contaminating the groundwater, depleting fresh water, degrading air quality, triggering earthquakes, causing noise pollution, it's very loud, causing surface pollution, and hazards to public health and the environment. There's a lot of lawsuits right now going on about fracking. So the cocktail is chemicals that are not disclosed by the companies that do this. So they won't tell us what it is because they say it's proprietary knowledge. So people are suing to know what are people injecting into my groundwater right next to my house. Over 1 million frack jobs have been done in the United States, and we'll see if this continues or if it's going to become illegal because of the environmental impacts, which are still unassessed. But a lot of people think they're causing little mini earthquakes everywhere. That's why we're having a lot of earthquakes in like Oklahoma, Kansas, places like that that normally don't have earthquakes. All right, we're going to stop this video there. And next up, we'll talk about balancing chemical reactions. All right, 107, thanks.